Have you ever stared up at the sky during a thunderstorm, completely mesmerized by the raw power of a lightning bolt? It's one of nature's most spectacular displays. Now, imagine a lightning bolt 1,000 times more powerful than anything you've ever seen on Earth. Welcome to Jupiter, the king of planets, where the storms are as colossal as the planet itself. For decades, we've known that Jupiter has lightning. The Voyager 1 spacecraft first gave us a glimpse back in 1979, capturing those telltale flashes on the planet's night side. But it took NASA's Juno mission, which arrived at Jupiter in 2016, to truly pull back the curtain on this atmospheric mystery. What Juno found has turned our understanding of planetary weather completely upside down. On Earth, lightning is a creature of the tropics. The sun beats down on the equator, heating the air and water, creating the warm, moist updrafts that fuel massive thunderclouds. So, logically, you'd expect Jupiter, which also receives the most direct sunlight at its equator, to follow the same pattern. But Jupiter, being Jupiter, loves to break the rules. Juno's instruments revealed something astonishing. Jupiter's lightning almost completely avoids the equator. Instead, the vast majority of its powerful flashes are concentrated near its north and south poles. Think about that for a second. It's like if all of Earth's thunderstorms decided to pack up and move to Antarctica and the Arctic. It makes no sense, right? Scientists were baffled. Why does Jupiter's atmosphere prefer polar lightning? This is one of the biggest puzzles in planetary science today. To crack this case, we have to look deep inside Jupiter's turbulent atmosphere. Unlike Earth, which gets most of its heat from the sun, Jupiter is so massive that it generates a significant amount of its own internal heat, left over from its formation billions of years ago. This internal furnace is constantly churning, radiating heat outwards from the core. At Jupiter's equator, the combination of intense solar radiation from above and the powerful internal heat from below creates a remarkably stable atmospheric layer. Think of it like trying to boil a pot of water by heating it from both the top and the bottom. It's not very efficient. This stability prevents the massive convection currents, the turbulent mixing of warm and cool air that are necessary to build up the electrical charge for a lightning strike. The air at the equator is just too settled to create the kind of towering thunderclouds we see on Earth. But things are completely different at the poles. Far from the equator, the sun's rays are weak and angled. Here, the primary source of heat is the internal engine of Jupiter itself, radiating up from below. This creates a massive temperature imbalance. The warm, moist air deep within the atmosphere has a clear path to rise, unobstructed by solar heating from above. As this air rises, it cools, and the water vapor and ammonia within it freeze into ice crystals. This is where the magic happens. Just like in Earth's thunderclouds, these ice crystals swirl and collide violently in the powerful updrafts. This friction strips electrons from the crystals, separating positive and negative charges. The top of the cloud becomes positively charged, and the bottom becomes negatively charged. When this electrical potential gets strong enough, boom, a supercharged lightning bolt, a megabolt, flashes through the Jovian sky, discharging that immense energy. And Juno didn't just tell us where the lightning was. It told us what it was made of. The data suggests that Jupiter's lightning is powered by a slurry of water and ammonia. Scientists call this slushy mixture mushballs. These ammonia-rich hailstones are crucial. They act as a kind of atmospheric antifreeze, allowing water to remain liquid at much colder temperatures than it would on Earth, down to about -100 degrees Celsius. This extends the region where lightning can form, creating the conditions for these incredibly powerful discharges in the upper layers of Jupiter's atmosphere. So, the mystery of Jupiter's polar lightning comes down to a cosmic balancing act. The planet's own internal heat, which stabilizes the equator, is the very thing that destabilizes the poles and drives the powerful convection needed for these epic storms. The sun, which is the primary driver of Earth's weather, plays a much different, more subtle role on the gas giant. What's even more fascinating is that this isn't just about lightning. Understanding Jupiter's weather helps us understand the dynamics of gas giants everywhere, including the thousands of exoplanets we're discovering across the galaxy. Each flash of lightning on Jupiter is a clue, a piece of the puzzle that tells us about the composition, temperature, and dynamics of its deep, hidden layers. It's a natural probe into a world we can't otherwise see. The Juno mission continues to orbit Jupiter, gathering more data with every pass. We've solved the big why of its polar lightning, but new questions always arise. How deep do these storms go? What other strange chemical reactions are happening within them? Jupiter is a planet of endless wonders, and its lightning is a brilliant, flashing reminder that the universe is full of mysteries just waiting to be explored. So the next time a thunderstorm rolls in, think of Jupiter. Think of its colossal polar storms, its ammonia mushballs, and its lightning bolts 1,000 times more powerful than our own. It's a great reminder that even in our own solar system, there are still strange and beautiful worlds that defy all our earthly expectations. Thanks so much for joining me on this journey to the King of Planets. If you enjoyed this deep dive into cosmic weather, don't forget to hit that like button and subscribe for more adventures into the mysteries of our universe. Let me know in the comments what other space mystery you'd like me to explore next. Until then, keep looking up,